Let's suppose we have a charge Q located here. The electric field at this point is given by this vector E. In a previous video we saw that the electric field at a point is the force on a charge of +1 coulombs at this point. So if Q happens to be +1 coulombs, then the electric field at this point is the same as the electrostatic force vector at this point. If Q is equal to +2 coulombs, then the electrostatic force vector, which I'm calling F, at Q, on Q, is equal to 2 times the electric field at Q. If Q is, say, -2, then the force on Q would be -2 times vector E. That means the force on Q would actually be in this direction here, opposite to the direction of E, and the magnitude of this vector would be twice the magnitude of E. Now in general, the force on Q is the charge Q, whatever it is, could be positive, negative, times the electric field vector E. Now let's suppose that Q moves a tiny distance in a certain direction. Let's suppose it ends up at this point here, and suppose that this vector is in the direction of this vector here, which I'll call S. Then since this vector is a little piece of vector S, the displacement vector, we can call this vector ds. Well, more correctly, we should really call it delta S and then consider limits. But here we'll just call it ds. So we can assume that we're after taking limits. So Q moves along this direction here. Now, what forces cause Q to move from here to here, we are not too interested in. However, we do know that this electric field E is acting, but there could be other forces acting. Or Q could already have been moving due to some other forces, and it moves from here to here, this distance ds, this vector, along this vector ds. Now we are interested in the work done by the electrostatic force F, not the work done by any other forces that could be acting on the charge Q. Now what I will do is I will show vector F instead of vector E. Vector F is along the same line as vector E, since it's just a scalar multiple of E. Of course, it could be in a direction opposite to the picture that I'm showing here, if Q happens to be negative. Okay, so vector F is in the same direction as vector E. To get the work done by the electrostatic force F, and only by this force F, as Q moves from this point to this point here, we have to get the component of F along the direction in which Q moves. So we need to project the tip of vector F onto the line containing vector ds. So this is the component of the force. Now, the work done by a force as a particle moves a distance ds is the component of the force in that direction times the distance that the particle, or well, the charge here, moves. So let's suppose that this angle is theta. So we have to take F cos theta, that's the component of F in the direction of vector ds, and multiply it by the distance that the charge moves, which is ds without an underline. So ds is just a magnitude of this vector ds shown here in green. Now it's assumed that as the charge Q moves from here to this point here, the force vector F doesn't change. Now there could be other forces acting, they might change, but we're only interested in this force vector. It's important that this remains constant. That means its magnitude and direction remain the same. So say when Q is at this point here, then force F on it must look like this. These two vectors must be the same. That's important. So we have to make sure that ds is small enough for that condition to hold. So we can say that we have a constant force F cos theta acting as the charge Q moves from here to here. F without the underline is the magnitude of vector F in the direction of ds. Okay, so this is the work done, which we can call W. We can of course write it like this. These quantities are just multiplied together. But now, notice that this thing here is nothing other than the definition of the dot product of vector f with vector ds. The dot product is the product of the magnitudes of the vectors times the cos of the angle in between the two vectors, which is theta. Finally, we can write q times e for vector f. Q is just a scalar. Okay, so there it is, the work done by electrostatic force F. Now, you will often see a minus sign in front here. You might see the work done written like this. Now, it's important to realize that this is not the work done by vector F. It's actually the work done by a force that's opposite in direction but equal in magnitude to vector F. Okay, so here is vector minus F. So this is a force that counteracts the electrostatic force acting on the charge Q. To see that this makes sense, to get the work done by minus F, we need to get the component of minus F in this direction here. Well, that's just got by multiplying minus F by the cos of the angle between the two vectors. But if we call this angle A, then the cos of A is actually the same as minus cos theta, because A plus theta is 180 degrees. So if we wanted the work done by minus F, we would have the cos of A in place of, we would have A in place of theta, but the cos of A is minus cos theta. We'd have a minus sign here. And the thing inside the square brackets is F dot ds. So basically the component of minus F along the direction of motion of the charge actually opposes the motion of the charge. So we could say that the work done on the charge by minus F is negative work.